Listo, profesor.
Ok, buenos días a todos. Vamos a dar inicio a la charla de cada sábado organizada por la red LAFMAT, Red de Física de Materia Condensada y Ciencia de los Materiales. Esta red está conformada por investigadores de diversas universidades de Latinoamérica, por ejemplo, Argentina, Bolivia, Brasil, Chile, Colombia, Perú, Venezuela, Costa Rica y México. Es un placer hoy poder introducir al profesor Neil Allan, quien nos dará la charla titulada From Structure Prediction to Combating Heavy Metal Pollution. Previo a su charla, voy a dar una breve introducción, una breve bibliografía del profesor. El profesor Neil Allan obtuvo su licenciatura y doctorado en química en la Universidad de Oxford. Posteriormente trabajó 4 años en la empresa ICI, Chemicals and Polymers, que en aquel entonces era la compañía más grande del Reino Unido. Posteriormente se incorporó en la Universidad de Bristol el año 1989 como profesor asistente y desde el año 2023 es profesor, full professor de físico-química en la misma universidad. Con respecto a la investigación, el profesor tiene aproximadamente 40 años de experiencia en química computacional y simulación de materiales de interés tecnológico, industrial y geológico, utilizando una amplia variedad de técnicas teóricas que van desde simulaciones atomísticas de redes cristalinas hasta cálculos de estructura electrónica ab inicio. El profesor Neil Allan tiene más de 250 publicaciones WOS y ha participado en numerosos proyectos de investigación, tanto como investigador principal como coinvestigador. Tiene intereses particulares en la termodinámica de efectos, sólidos no estequiométricos y soluciones sólidas en cerámicas y minerales. En particular, se puede destacar el desarrollo y aplicación de nuevos métodos para realizar cálculos termodinámicos, tanto a través de programas de dinámica de red como de simulaciones de Monte Carlo. Y a través de los años, el profesor ha sido capaz de predecir nuevos materiales, como por ejemplo el óxido de zinc con estructura tipo grafeno, que posteriormente fue sintetizada y caracterizada experimentalmente. Las predicciones recientes que él ha hecho incluyen posibles nuevas soluciones fotocatalíticas con anchos de banda ajustables y materiales de boro oxígeno ultra flexible. También en cuanto a gestión se puede destacar el hecho que fue presidente del CCP5 en Reino Unido, que es un proyecto nacional del Reino Unido colaborativo para la simulación de materia condensada, que se dedica al desarrollo de software y organización de escuelas de verano, las cuales están entre las más grandes en Reino Unido, en tópicos tales como termodinámica estadística, dinámica molecular y métodos de Monte Carlo. Él ha colaborado estrechamente con investigadores de Sudamérica. A él particularmente le gusta destacar su posición como profesor visitante en la Universidad de Buenos Aires. También se puede destacar algunos proyectos colaborativos con investigadores colombianos y chilenos, principalmente en la remediación de aguas contaminadas con metales pesados. El profesor Neil, como dije recién, él habla español. Si ustedes pueden hacer preguntas si hablan claramente, él les va a poder entender las preguntas. Él va a dar la presentación en inglés, pero después las preguntas pueden ser tanto en español como en inglés. No sean tímidos, please, no, don't be shy. Miss Neil, when you feel ready, you can start. Puedes comenzar cuando te sientas preparado.
Oh, ah, hola a todos. Muchas gracias por la invitación y muchas gracias también a Sergio para la presentación. Ah, y hola desde Bristol, en Inglaterra, en el invierno. Hace muy mal tiempo. Anyway, ahora voy a cambiar el idioma. Voy a hablar en inglés. So voy a compartir la pantalla. ¿Es okay?
Sí, it's
Big
okay, Neil.
screen, all right?
Yeah.
Mm.
Yeah. Well, welcome everybody. Thank you very much for the invitation. And as Sergio says, I am a professor of chemistry at the University of Bristol, which is the largest city in the southwest of England. And what I'm going to do today is talk about a number of quite varied applications which we have done in the past and which we are following up on. So I am just trying. Yeah, there we are. Right. So Bristol, as I said, is the largest city in the southwest, and perhaps it is most famous for this suspension bridge, which is one of the first suspension bridges built across the River Avon back in the 19th century. It took many years. It was designed by the famous engineer Isambard Kingdom Brunel, but then there was no money, and for many years nothing happened. And unfortunately, he died, but then it was completed by others in his memory. But there are other famous features of Bristol. There is a famous balloon festival every summer. It was also famous for designing the aircraft, the Concorde. So there is a big tradition of aerospace engineering in Bristol. There's a special museum for science outreach for children, a museum for children and science down here, which I show the outside of this in the bottom left. And this is one of the big hills in Bristol. It is like Rome, which is built. It's a lot of hills in Bristol. There are 7 big hills, just like Rome, and this is the big tower. It shows the big tower of the university. That's not as old as it looks. Bristol University is about 100 years old, and that's why. But that's where much of the activity of the university takes place. So what we're going to start to talk about today, we're going to talk a little bit our predictions of structure. One that we did rather a long time ago now, and then I'm going to talk about our latest prediction. Then we'll move and talk a little bit about work we do on ions which are moving. About ion conduction, oxide ion moving in a complex oxide. And then rather interesting result about noble gases in oxides at very high pressure. And finally, because of the work that we do with Chile, with Sergio, but also with a group in Barranquilla in Colombia, we will talk about a very applied project we're doing on which is making nanoparticles to remove nasty heavy metals from water. And a very good question you might ask is, why are we working on all these different projects? Well, the answer is that we've managed to get money for various different projects over the years. It didn't quite work. wasn't intended. Some of them we've just thought were interesting, and from others. So that is why the subject is very varied. Now, before we start on the structure prediction, what I did want to say was I think that a big role of theory is both to understand at the atomic level what is going on in experiments, and so help experiments design, help people doing experiments design their next experiments, but also you to live a little dangerously and make predictions. And here is just a list of some of our predictions over the years. We've made other predictions that still haven't been proved experimentally. But I think the other side of that, I don't think that it's that people who do computations should restrict themselves just to reproducing numbers that that experimentalists produce in their experiments. Of course, that's very important to test methods and develop methods, but I think there is, and increasingly with the powerful computing and machine learning, I think it's part of the, we're now entering another age when theory can actually drive the science forward much more directly than ever before. So our first structure prediction is zinc oxide. And this started over a cup of tea. Cups of tea are very important in Britain. There is the afternoon tea time. And I was talking to one of the other professors of physical chemistry here in Bristol who grows zinc oxide. Or used to grow zinc oxide crystals, and he was puzzled by seeing this 0001 surface so prominently in the crystals he was growing. And I agreed that we would do some calculations, which I said would take a week, and in fact took several years. Now, what's special about the 001 surface is an example of something called a polar surface. So in principle, it is unstable because there's layers of cations, anions, cations, anions. There is, in a thin film, there would be a dipole moment perpendicular to the surface, and there would be one in a unit cell and then one in the next unit cell, in principle, and then giving an infinite energy. So something happens to remove that dipole. In England, we tend to call it, after somebody first pointed that out in this country, the Tasker classification. Other people refer to it as the polar catastrophe. Well, we started off, and a student of mine, well, actually two students of mine, were working on these surfaces, and we did thin films, and using GGA, density functional theory back then, they were optimizing the structures of the films. And when it came to this 0001, what happened is that the structure changed very, very hugely. And I said, I don't believe it. I mean, the bulk structure of diamond is, the bulk structure of zinc oxide has all the atoms in tetrahedral coordination, with the zinc tetrahedrally coordinated and the oxygen tetrahedrally coordinated in a structure called the Wurtzite structure. But what we were finding for these 001 films were actually the cation and the anion rings were collapsing into, layers were coming together, forming hexagonal rings, as we show here. And so they repeated it over and over again. I could find no references to it in the literature. And eventually I said, you must be right, I'm wrong. which is something that students like to hear. And then actually it made sense. Thought about it a little more, and it made sense, because physically what was happening is that the layers coming together removed this dipole, because now each layer had an equal number of cations and anions. And actually, it wasn't that unusual anyway, if you think of the chemistry of carbon. Now, if I was to take that Wurtzite structure and replace all the ions with just carbon, I would be actually forming one of the forms of diamond. And then it also struck me that, well, in carbon you have graphite and graphene. So why can't you have the same sort of different structures formed by these Wurtzites? So we were brave enough, and I should say both those students did forgive me for not believing them. They're both one's a professor and one's an assistant professor at another university in Britain. And so we showed that for thin films, that the structure, well, for a single structure, it would be a graphene-like layer, hexagonal type of layer. And for that was actually the lowest energy for films of about up to 18 layers. And of course, just like graphite is different from diamond, so these films have very different properties from that of the bulk zinc oxide they're photocatalysts, apart from other things. So altogether, it's an excellent example of how nanoscale structures are very different from the bulk. And we were brave enough to predict this form, and then we waited 2 years, and then this is the first experimental report, I would say, that came out. Authors with whom we had no, I didn't know them then, I don't know them now. And of course, we went on and developed that by looking at a lot of other compounds with the Wurtzite structure, apart from zinc oxide and zinc oxide. We looked at zinc sulfide, other sulfides, other oxides, all behaved rather similarly, forming in these potentially forming these graphene-like thin films. And the most recent study, which we've been doing with Sergio, has been actually on silicon carbide and on the energy landscape of these thin films. Now, looking at it more recently, which we started almost 20 years after we first started to look at it, we do have a more complicated picture emerges. There is these energy landscapes are really very complicated, turn out to be very complicated, because there's a balance between trying different ways of removing the dipole, which may involve atoms moving or charge transfer, and different things happen preferentially at different film thicknesses. So there is another structure predicted for intermediate film structures in some of the cases, which is in the original Wurtzite structure. You can think of the 6-membered rings as like cyclohexane. You can tell that I'm a chemist by those sorts of analogies. But cyclohexane in the chair conformation, whereas in this BCT structure, we form 6-membered rings in which the 6-membered rings, they're like cyclohexane, but this time in the boat, in the boat conformation. And very recently, again with Sergio, our host, we found that there actually is one of these graphitic forms is rather interesting, because actually they're just staggered relative to, because of course with these rings, the 6-membered rings, they can be stacked in different ways. And there is a staggered graphitic form in which actually the top of the films are still not the same as the bottom. And for that one, this one structure, the band gap changes, reduces markedly with thickness, much more than for the others. Down to, and for example, in the silicon carbide example, we get down to an absorption in the visible region. So all of that is really quite a test, and a test for experimentalists to come out. But now there's a lot of research going much more on these very thin films than when we started off. Right, a more modern example, just very close off we've done very recently, is quite different. And again, it started by accident, not a grant application or anything like that. Another cup of tea with one of my inorganic colleagues, now retired, who was making boron monoxide, BO, and we wanted to know what structures that might do. And so we did that. But then we started looking at boron examples, more boron chemistry of boron oxide and different structures more generally. And what we first did of that, so we moved away from the rather esoteric boron monoxide simply to boron oxide, B2O3, the well-known one. And first of all, we predicted very flexible, low density, porous forms of B2O3. And actually, there's loads of these. But the key bit that people had ignored was that the boron, if the boron is 3-4 coordinate, the boron oxygen bond angle is very flexible. That's unlike the covalent bonds that you learn at school. It's a bit silicon, oxygen, silicon is rather similar. But the angle, so if I just take, for example, BH2O, BH2, it's the difference between that bond angle in energy between C2V and D2D is really very small. And if you're a chemist and you've done organic chemistry and you can know about valence bond and resonance hybrids, you can do a back of the envelope model to rationalize that, which we've done at the top here. That's not so, but to extend that to the solid state, as we did, we managed to say that there were a lot of structures that you could build up for boron and oxygen. And they would have a very flat energy versus volume curve. Very flat indeed. More characteristic of those associated with MOFs, or metal oxide frameworks, which are so fashionable these days. But of course, here there is no organic molecule, organic at all. But one of the crucial things was that we predicted is that these were low in energy. They were about the same energy as the known phases of solid state phases of boron oxide, alpha B2O3 and beta B2O3. And that's, I mean, people have predicted nanoforms for all sorts of oxides, including zinc oxide, but they're all massively high in energy. It would be very difficult to form. Now, historically, and I should say this is before my time, back in the 1960s, there was a huge controversy about the density of molten B2O3, because it seemed to be that depending on how you prepared it, the conditions, you could get a big variety in the density. Well, our results suggest why that will be, because there's lots of different forms. Depending on the conditions, you'll get different ones, and there's a lot of flexibility in the bond angles. So depending on the precise components ones you've made, the density may change quite a lot. And apparently, historically, that was quite a bad-tempered controversy. And I particularly feel sorry for, there was a graduate student who, I can't remember, either at Imperial College London or at University College London, who was given the task of constructing a physical model. And of course, that was doomed to failure because they assumed you always had a rigid BOB bond angle. And apparently the model fell apart before they finished the PhD. So I'm not quite sure what happened there. But now, however, we've extended that. And one of the things we've recognized is that if you take any silicate based on SiO2, which is based on SiO4 tetrahedra, now that's SiO4 4-, we can replace that with B2O5 4-. Okay, that's not a tetrahedron, but at the two ends, the oxygens are arranged with the same orientation as they would be in the tetrahedron. Okay, there's an extra oxygen in the middle. But in principle, we can do this substitution. So we can take anything with either idealized formula SiO2 and turn it into the corresponding boron compound. And first of all, this is not a zeolite, but we tried taking beta cristobalite and turned that into the borate. And here are the energy versus volume curves calculated a few years ago. We did a few years ago, first for the silicon and then the new boron equivalent. And you can see that, I mean, the silicon-oxygen-silicon bond is flexible, but so is the boron-oxygen-boron, as we have seen. So the minimum energies, so you can see if we look at the purple curve, that's very broad. So very recently, we've started looking at zeolites with a former PhD student of mine, now based in Thailand. And so we can replace all the SiO4s with B2O5s. Here's some pictures of the result, having generated the new ones. Again, this was actually some PBE calculations. I'm going to come on to dispersion briefly later. We tested the methods on the zeolite, the original silicate zeolite, reproducing lattice parameters and structures well. We had a paper had appeared saying, which is, I still don't, which actually I frankly disagree with, saying, because in our original papers on the boron oxides, we had ignored dispersion effects. And they were using a program I'm not going to name, and I think there was simply a bug in the program they were using, because we have included dispersion corrections, and as you would expect, I think, for something as light as boron, they make a difference, but not a huge difference, and no qualitative conclusion of our work changes. And the conclusion from that the boron zeolite structure is not that much higher. The formula of that is B2O3 again, is not that much higher than that of the known structures of boron oxide. Here are some of the energy versus volume curves for the known oxides of boron oxide, with and without the dispersion corrections. They become slightly narrower, the curves, when you include the effects of dispersion. And now we have, on this next slide, we have the energy volume curves for the alpha form, the beta form, and then our zeolites. And yes, there is the boron zeolite, the minimum energy is a little bit above that for the alpha and the beta known forms, but not very much so. And here is a comparison of the energy versus volume curves for the boron zeolite relative to the AFI zeolite. And again, we see that the boron structure is actually a little bit more flexible, has a wider curve, it has a larger, the curve is broader than that for the silicon equivalent. So that's our conclusion, that we've built in some chemistry about the flexibility of the BOB bonds to predict new forms of boron oxide. It solves this old tempered problem about the density, but for me the interesting challenge is to see whether someone could construct zeolites based not on silicon but on boron. Now, I mean, I know zeolite synthesis is a very specialist thing. I mean, that's what people do, that's their career. When I worked with a big company, we had somebody doing that. So that's a huge challenge. I do just want to bring in an acknowledgement to say all those calculations on the zeolite were were in conjunction, well, in collaboration with my Thai student Euclid, but they're all carried out, and the geometry, how to do those substitutions of SiO4 with B2O5 were all worked out by he teaches at a specialist science school. So they were all worked out by a set of his 16 and 17-year-olds that he's teaching at his school. So I'd like to thank them even at this stage. They were very impressive, school pupils. Now, we also do calculations on atoms moving, and I'm going to talk about two applications of ab initio molecular dynamics on quite complex materials. And the overlying theme with most of the examples are where I've been wrong in advance. And here we have bismuth, complicated bismuth and vanadium oxide, which is actually one of the best oxide ion conductors. So the oxide ions are very mobile. And it's got a very complicated structure, but all we need to know is it's got layers, vanadium oxide layers and bismuth oxide layers. And because we'd worked on the local structures and the local environments in the delta form of bismuth oxide before, and rationalized the conductivity there in terms of the ready distortions and the local environments of the bismuth ions, I said, well, yeah, I don't think the vanadium is doing anything special. It's all in the bismuth. We'll find it's all in the bismuth layers. Actually, that was the papers, even the structure wasn't fully resolved in the literature. Very little was understood about this structure. We looked at a lot of possible local arrangements, both by doing minimizations of possible structures. And there, that started to indicate that I was going to be wrong, because first of all, we found that basically oxygen vacancies were not going to be in the bismuth layers, but in the layers where there were vanadiums. So that started indicating that actually the vanadium oxygen layers were very distorted. And indeed, what we saw was that the conduction was didn't involve really the bismuth layers at all. I was wrong. This picture here shows, and these two pictures, so some of the ways the oxygens, basically how the oxygens move, helped by the oxide vacancies that are in these vanadium oxide layers. And round the purple ions here, not much takes place. They do help the conduction along by moving and distorting as the oxygens move around the edges of the vanadium layers. And but the oxygens within the bismuth layers, the one that I predicted would be important, aren't important at all. And I have what I'm pleased about is that I have seen a preprint, but I don't think it's come out yet, of a very exhaustive study of this system recently, which actually it's a combined neutron study, X-ray diffraction study, very detailed experimental analysis, more than anything done in the past, which I'm happy to say gives results all consistent with our model. So these days, our calculations are able to really reveal useful information, reliable information about really very complicated systems. One of my hobbies is looking at minerals, because I've talked to earth scientists for many years. And a project that we used with my collaborators, long-term collaborator in Norway, is looking at noble gases, this time in a simple compound, magnesium oxide. That's an important geological question, because it tells us where the noble gases come from and tells us about the circulation in the deep earth. And they looked at basically neon and helium. And I certainly predicted, I said, well, of course, helium in the bulk is going to move much quicker than the neon. And that's what that's what the models of the geologists currently assume. But having run the ab initio molecular dynamics, admittedly in small cells, over a range of temperatures and a range of high pressures, going up to 100 gigapascal, which is the pressure at the top of the Earth's core. Under most situations, if you look at the green neon curves and the red helium curves, the neon is moving faster most of the time, under most situations, under not necessarily always, but most of the time, particularly at the higher pressures, which was counterintuitive. We also did nudged elastic band calculations, which showed the activation energies for the atoms moving, that suggested the same thing. We even added argon to our list. There. That was counter. That's not what we expected. I don't have time today to give our detailed explanation, but I would say that it's a bit like, imagine a shop full of china, sort of plates and cups and things, and I've got an elephant called Neon in it. Well, actually, the elephant is unhappy in the shop, but it's pretty easy for the elephant to move anywhere. It just causes chaos and strain wherever it goes. It doesn't really matter very much on its position. Whereas having the helium, a better model would be having a cat in the china shop. Not entirely happy, but it can it does have, there is then more of an activation energy. Some positions are happier, it's happier in some positions rather than others. A key thing is it's because of the simple structure, there is a large change in its coordination number from 8 at the equilibrium position to 4 at the interstitial, the transition state for the migration, that turns out to be important. And it's not the same in other structures like the Bridgman, like the magnesium silicon perovskite that makes up most of the lower mantle. It's not. The behavior is the other way round. And we know why that is as well. It's due to the flexibility of the perovskite structure. But the conclusion for this is the very dense minerals. We think that diffusion, maybe rather models of this diffusion, at least for noble gases, is rather different from what has always been assumed. And finally, what we've been doing, a much more applied project that we've been doing with Sergio in Chile and with Carlos Pinilla and his group in Barranquilla in Colombia. The object is to remove heavy metals. Typically in Colombia, it's mercury from illegal gold mining. In Chile, it's more lead and cadmium and bismuth, things that come off from the mine waters from the big mines, the big copper mines, the big lithium mines. And the idea there is to have an iron oxide, a magnetic iron oxide core, surrounded by a silicon oxide surface on which we tie functional molecules, organic molecules, that will eat up the nasty metals. And as an inorganic textbook, or as our relatively simple molecular calculation showed, the key thing for that is to have some sulfur atoms in the organic ligands. Typically, the ones that turn out to be best are thiols, which are basically SH groups. Now, it's all very well us designing something, but you know, people have to make these things, and my colleague Sean Davis and the Sergio's colleagues in Chile have been making these things. In Colombia, we've been investigating simply taking the thiols, the molecules, from local fruits and vegetables, whereas in Chile, the organic chemists have been designing molecules similar to those in paper making to make those. And here are some preliminary results from some made in Chile, where, these nanoparticles are getting rid of the lead, the cadmium, copper and mercury, as you would expect chemically, hopeless for something like boron, hopeless for arsenic as well, because the aqueous chemistry of arsenic is quite different. And there's lots of problems, other problems around recycling, reusability, how to scale this up. But certainly, in terms of designing a system for the bottom up, so far the project is working nicely. So I was told I could go on. I've gone over by a few minutes too much, so I'm sorry about that. But what I hope is that I've talked to you a little bit about our simulations, both of structures, one of the thin films where our predictions were verified. I've made quite a interesting, what I hope is an interesting prediction about new zeolite type materials based on boron and not silicon. I've given two results of atoms moving and how they move, where the results were not what you would have expected. Well, not perhaps I should just say not what I expected anyway. And also I've talked very briefly about our more applied project, which is on removing heavy metals from water, that is very different from the theory, but from the normal stuff I do, but is highly enjoyable. So that really leaves now to me to thank an enormous number of people who I can't mention, all over, both in South America, in Britain, and Norway, also in Europe, in Norway and in Thailand. So this means I come to the end, and I'll just say muchas gracias a todos. Thank you.
O'Neill, many thanks for your presentation. Was a very good and very clear presentation. So now some questions will be asked by the invited panelists. So we are going to start first with Professor Stuart Holmes from the University College London. Stuart, do you have? Okay.
Thank you. Thank you, Professor Allan. Very interesting talk. You mentioned the zinc oxide. Is the catastrophe particular to that surface? Is the symmetry of the surface important for the catastrophe?
Yes. Yes, because that you can classify ionic surfaces in three ways. And this catastrophe is due to a guy who worked at Harwell called Phil Tasker, and there are non-polar films, type 1 and type 2, which don't do this. This is the type 3, and the simplest one that will do it is where you have cations, anion, keeping the formula, the stoichiometry the same. You see cations, anions. So the top of the film will be plus, and the bottom film will be minus. So the classic example, the simplest example, is the 111 surface of sodium chloride.
Oh, I see.
Which you have to grow with. You have to do something. So usually surfaces will change, or you add a modifier or something. So you have to put urea in when you grow your sodium chloride crystals to get the octahedra forming. You have to add urea to it. So that's probably the simplest example that you've met in a different context. So it's by no means restricted just to this one.
But the reason I'm interested in these materials for making so-called two-dimensional electron gases, and on the zinc oxide surface you can get very high mobilities. If you put a zinc magnesium oxide cap on, you can get very high mobilities. But I think consequently you also get very high carrier densities because of this catastrophe.
Yeah, indeed, because what happened, one of the mechanisms, there's lots of things that can happen.
Yes.
You can have ions can move, you can have steps, you can have ions flat out, impurities coming in, but the other way is to have an electron transfer, change of oxidation state, forming a metallic layer that's somewhere, and then you get all this very interesting electronic behavior that you are interested in.
I'm tasked with trying to make devices in that, or will be tasked in future grant applications.
Yes.
Thank you, Professor Allan. Very, very interesting talk. Thank you again.
Thank you.
Thank you for answering my question also.
Yeah.
Okay, thank you, Professor Stuart Holmes. So the next invited professor is Professor Prashant Rai from India, from the University of Mizoram. Professor Rai, do you have any question?
Hello. Can you hear me?
Yes, we can hear you. Please, can you switch on
Thank you.
your camera?
Thank you, Professor Allan, for the very nice talk, and thank you, Professor Louis, also for inviting me to join this nice webinar. So I have a few questions. I'm very much I like the line. It says God makes solids, but surfaces are devil's work. Can you elaborate this thing?
Oh, yeah. Yes. Well, I didn't make that up. I think there are in my you can interpret that in various ways. You can interpret that in terms of simply some of the physics becomes very complicated. There are lots of different possibilities. When I work and allowing for those my friends who work on crystal nucleation and crystal growth, that's a very, very difficult. They're all very difficult problems. I found it's curious. I think, when I worked in industry, a lot of people wanted to work on catalysis, but a lot of the catalytic processes that have, of course, involved surfaces, but actually being able to model a surface that made any difference, that was similar to the one that they might have experimentally, certainly in a plant, was really almost impossible. So I've almost completely avoided catalysis in my research career, with one recent exception. Even in the other issue, of course, applies to when we try and model, for example, interfaces more generally. To what extent, when we look at diffusion results that are produced experimentally, actually, should we just be looking at grain boundaries rather than in the bulk? That's actually a huge problem for us in our work on incorporating minerals more generally in the geology work. It's all very well us worrying about the noble gases in the bulk, but if actually the bulk of diffusion is up through grain boundaries and interfaces, am I really doing something? Am I really being useful?
Okay, thank you. I have one more question. So, I've seen in your the NAB curve, right? That new elastic bands, the barrier potential is bigger for the helium, though helium is a lighter element. Suppose,
Yes.
what is the physics behind that? Why it is
Right. Okay. In our manuscript on this is under review, and I'm not. I'm trying to think how I can summarize a page for you. What it boils down to two things. There are various terms that contribute. There is the strain in the lattice. So we did calculations showing the strain in the lattice, having removed the noble gas, but it's at the same optimized coordinates, allowing for that caused by. So we've just taken the noble gas out. So that's one term. Actually, even there, the different in strain. So that's one term that contributes. The other term is simply the repulsion between the noble gas and the lattice. Now, they're actually, both helium and neon are highly squashed. And I sort of alluded to this when I was saying that the special thing about the transition state is that there's only 4 neighbors at the close neighbors at the transition state. And that means that the neon, which is particularly large, we're very much on the repulsive wall of the potential. And going from 8 to 4, even though, of course, the neon is larger and that's a big repulsive interaction, we've lost some of the repulsions. We've lost those 4 repulsions. And that's what makes a big difference to the overall activation energy, which I can view as a sum of this strain term plus the interaction of the noble gas with the lattice. That's a brief summary for nothing. I'm sorry, I have to wait till our paper appears. I'm actually got very interested by that, and I'm writing a little review at the moment called When Heavy Things Move Faster Than Light Things, because there's all sorts of interesting reasons why that happens.
You mentioned like there is a repulsion, like interaction is like a repulsion type of interaction. Like you mean it's a Coulomb potential? Generally inert like these are like
well, it's the
non-interactive type of elements, right?
Yeah, it's the short. Well, in this case, that's right. There are the short range. In our case, this is the short range repulsion. Say that you're having a Leonard-Jones, but I mean, you know, that you having a Leonard-Jones potential. It's the short range electron repulsion between the electron clouds. Yes.
Okay. Yeah. Thank you. That's all.
There are, in the other examples, there are interesting examples where, you know, in alloys where features of the directions of the d orbitals can contribute. I mean, it's not that we've found that, but they're in the literature. And of course, you can have examples. There are examples we've got some examples of actually molecules diffusing through zeolites again. So it's an interesting counterintuitive argument sometimes.
Yeah. Thank you, and good luck for your paper.
Thank you. Thank you.
Thank you, Professor Ray, for your question. So now let's move to Venezuela with the Professor José Eduardo Arévalo from the Universidad del Zulia. So, José, do you have any question?
Sorry. No question. I just want to say thank you to for your nice and very didactic presentation. There are a lot of things that I never heard before about, but it was quite nice. Thank you for your presentation.
Thank you. Gracias.
Okay, thank you, José. So then, I'm going to ask to Professor Alfredo Tlaluises from the Universidad Autónoma de Nuevo León in Mexico. So, Alfredo, do you have any questions?
Oh, hi. Thanks for the nice talk. My question is regarding all the calculations you need to make just to make sure that you have a new structure, a new material, phonons, Ball constants. What is more important from all these calculations for you in the case of all these new materials that you propose?
I'm not sure I completely understand the question. I mean, how do we characterize them? Well, they have to be a minimum in the energy landscape. And what I didn't have time, of course, you have to test that there are no imaginary phonons. So they are genuine minima. They're not transition states. And if you satisfy that, then we are satisfied.
Yes, that's the lattice stability, right?
Yes.
You can make, for example, the Ball constants, but maybe you can include these molecular dynamics calculations. So what's the more important, or what's the major weight from these calculations that you consider?
Sorry, what do you mean? Can I just ask you, what do you mean by the major weight? Do you mean which calculations do I trust more, or
right,
which ones? Well, I trust both of them. The problem with molecular dynamics, which is not just in materials, but in biomolecular modeling, is the fact the time scale is very limited. So I won't, you won't see a protein unfolding. I won't necessarily see, if it's unstable, it changing over a picosecond or a nanosecond to a new structure. That's why calculating the phonons, which is an important thing.
Thanks for your response. That's all for me.
Thank you.
Thank you, Alfredo, for your questions. So now let's move to Argentina with the Profesora Gabriela Grat from the Universidad Nacional de Córdoba. Hi, Gabriela.
Hello. Hello, Professor Allan. Very nice talk. Very very interesting. All the systems and the procedure. That's what I'm curious. How do you propose? How do you start studying the reconstruction? You go straight forward with the molecular dynamics, or you start first at 0 Kelvin, and then you see after the phonon?
Yes, a very excellent question. And I'm almost tempted to say, how much time do you have? Because it's, I mean, so with the surfaces, with the structure prediction, they are all static calculations. So we would start off, I mean, what we started off was simply, so with those films, we simply cut a section of the bulk relevant to the surface, and then you do an optimization and see what happens. Geometry optimization, but it's still completely static. So all those calculations on the surface come from static optimizations using a range of programs, which some over the years we've changed. Some have been plane wave calculations using programs like CASTEP, which is free for us in the UK, or Crystal, the Crystal code developed by Turin and Britain. So they're all the static ones. Any dynamics calculations, we simply set off with a simulation cell, say in the noble gases, which actually uses I'm happy to say, used a lot of Norwegian computer time and not British computer time. My collaborator there, that used the VASP program, plane waves. So we just set off a normal simulation cell of the bulk and put the ions in various places, put the helium, because there's a very obvious interstitial position there. And the static minimizations of the nudged elastic band were also carried out using VASP there. But in that case, it's really rather quite straightforward in that case of, MGO's got a very regular structure. It's not non-stoichiometric. It's quite easy to set up. But in a way, each problem gets set up in a different way. But most of them involved guessing a crystal structure and working out and then doing a geometry optimization. We don't have, there are other people who work with our structure prediction. Of course, they look at a lot more starting structures than we do. I'm a bit of an old-fashioned dinosaur chemist like that. I like using some chemical intuition in our structure prediction.
That we don't have the physicists, unfortunately.
Really? Yeah. Well, we haven't done. There are other people who do who will start off. And they do their crystal predictions. They will, first of all, they'll say, okay, if my primitive cell only had 2 atoms or 4 atoms, well, I've got A, B, C, alpha, beta, gamma, and the positions of the relative position. If I've got only 2 atoms, then there's not that many variables. So I can do that from scratch. I don't have to put any chemical intuition in. And the problem about that's fine, but you've made a big assumption about that your primitive cell only contained 2 atoms or 4. And my guess, we've always started off with a much larger supercell, looking at structures which at least obey chemical valency rules. So we haven't used so much computer time as the really ones right from the scratch, but then they can argue that as computer power comes on, they've looked in a much fuller way at all the different possibilities. You choose. It depends how much money you have for the computers.
And for instance, for zinc oxide, you said, I'm not sure if you said it in that case, but the reconstruction depends on how many layers do you have.
Yeah.
So you have to be very careful with that.
Yes, oh indeed. And you've got to carry on with the number of layers, and you also need to test not only the number of layers, but also make sure in some case that that the surface cell isn't too small either, because sometimes they might that can choose to rearrange sort of spontaneously too. So there is a balance.
You're using quantum espresso too. I've seen some slide where you.
Yeah, that's the program my Thai collaborators use. They've been using quantum espresso. We haven't actually been using that in Bristol ourselves.
And that's for molecular dynamics, or
yeah. Well, no, for that application, that's just static minimizations.
And for molecular dynamics, you use which one?
Molecular dynamics. Well, we use. Really VASP has been VASP. We have initio, but we do a lot of classical molecular dynamics, which we do with a UK program. There is actually a national molecular dynamics code called DL Poly, which was part of the CCP5 network that Sergio said I was the chair of. So we use that a lot of the time. We do also use LAMPs now.
LAMPs, yes.
But we have been using a lot of DL Poly, partly because another of my former students was a major developer of DL Poly. So I have a loyalty to my former student to use their program.
The thing with these codes like LAMPs is that you need all the possibilities of potentials, no?
Yes, well, indeed. I mean, and that's another whole issue.
Yes, that's
and something that I do not work on. Well, I have a student, jointly supervised student, who is looking at machine learning potentials for more complex simulations. And I think it's moving very quickly, and we can now in many examples move to using machine learning potentials, new ways of calculating, set up in different ways. And there's some very powerful results. But and there are groups in the well-known groups in the UK who are working on that problem. But we're not. We're just using it. We'll just be using it. I should say our experience with. I haven't talked about that here. He's looking with a student who's looking at ionic liquids. Is they're spending a lot of time generating these machine learning potentials. A lot of time, more than I thought they would, but would be necessary. But that's life. That normally happens in a lot of projects.
Yeah, that's this classical stuff is faster, but then you have
Yeah.
that
Yeah.
that big
Absolutely.
problem.
Well, you know, I've been around for a long time, so we have a lot of papers with classical stuff as well as the ab initio stuff.
And the last question about the last system, why did you decide to do these two? You put magnetita and on top silica. Why
Right.
did you decide to
Right.
do
Why
that?
did we choose that? Well, basically, the project started off in Colombia. And there, the idea was to use things as cheap as possible. And iron oxide you can take from the beach. I quite like excuses to go to the Caribbean beaches. It's rather nice. And it's magnetic. So in principle, that could help the engineering later on. That was really I gave you a semi-serious answer there, but that's the serious answer. And of course, silicon, I have colleagues here who make nanoparticles, a lot of experience of making nanoparticles. There's a biomimetic group here. So they have a lot of experience of that as well. And so basically the idea with it is to make it as cheap as possible. Now, if we have what I didn't mention, we have some Chinese students here working on similar sorts of problems, but there we're looking at something different. We're looking at resources that they have in China, like looking at natural zeolites that they have in have. So it's
So it's better to have these two layers, not just the magnetic one. You need the silica.
Yes, because we want to do the type. Actually, some of the molecules we're tying on it, which are actually have silicon in there in the organic molecule as well. So there is silicon. So at one end, you've got silicon attached to several OH groups, which then goes on to some carbons and the thiols. And that way you can attach, that way my experimental inorganic colleagues say that's easier to tie it to the silicon layer. I mean, it may change when we get on to thinking about how to regenerate the particles.
Okay, great. Thank you. Thank you very much. Very, very interesting. All the topics of your talk.
Thank you very much, Ren.
Thank you, Gabriela, for your questions. So now is the turn of Professor Mario Reis from Brazil, from the University Federal of Fluminense. So,
hello, can you hear me?
Yes,
yes,
very
good.
good.
Thank you. Thank you for your talk. Very, very nice, very interesting. My question is can be a bit naive because I'm not from the field, and
they're usually the most difficult, the best, and the most difficult.
yes. It's a general question.
Yes.
And we know that nowadays there are several techniques to achieve this prediction for material science and computational physics, computational chemistry to predict materials. And this field goes in a different pace of the experimental fields. And how do you see these different comparison of computational results and experimental results? This is my first question, your view about this, and how this can affect your particular work.
That's an excellent question. And you're asking me now, it is interesting. I mean, some of the attempts to predict, I've had a lot of big profile about predicting materials, have not been received very well by the experimentalists. I don't think I want to mention any names, but there is one famous example I know where a famous crystallographer from this country, wrote quite a robust reply, or just pointed out that the theory, some of the predictions were clearly not quite right, that they'd combined it with the experiment. Sometimes the experimental diffraction patterns did not actually confirm the structures that had been made, and sometimes there were claims that they'd made new structures, but actually the difference in space group between a known structure and theirs was so small that it didn't really count. Now, you see, you've got to allow for I'm a dinosaur, a bit of a dinosaur of a certain age, and I quite like, as a chemist, putting in some chemical intuition to this. And I think there is some way to go before I will be put out of business by that. Now, I stand to be proved wrong on that, because I said, to put this in context in a different field, I have a colleague who left the university to run a basically AI and machine learning company predicting drug design, which is extremely successful. I looked at the amount of which funding he has raised, and he has various drugs in quite advanced clinical trials, and I think he's proved me wrong in that field, because again, you're dealing with, is there enough data to where there's lots of data, reliable data, then of course AI and machine learning is making dramatic headways. But in ours, is it the biochemical processes are so complicated that I wonder, how would you get AI, for example, to design a new drug to try to cope with Alzheimer's disease? Now you'll be noticed that I've purposely moved from materials science and the inorganic structure prediction to a rather more difficult one. I think the advances in getting these machine learning potentials means that there will be a lot bigger part for theory and understanding. But for me, sometimes the biggest problem in relating the theory and the experiment is not really predicting a new material. It's trying to find a problem related to the application that you can actually solve.
I see.
That's not something that the computer can do, in my experience. Sorry, I'm giving you a long answer because I'm thinking.
I see. I understand. It's a application problem, application problem driven, and not in fact the basic science. You mean?
Yes.
I see.
So rather difficult. I mean, I've had that problem all my career. From the time I was sent down, I was sent very early on, in sort of 40 years ago. I remember I was sent down to a chemical plant because my manager said, "Oh, you might be able to do something useful there." And I said, "What's in the vat that produces some polymer or something? What's in the?" And they said, "We don't really know."
Yes.
And that was an extreme case. And apparently it was important that whoever was the engineer on duty smoked. So the cigarette ash even played a role in the catalysis. Now that's a very extreme answer where theory wasn't able to contribute. Where I was able to contribute, even though all those years ago in industry, was have a model for the lifetime for hydrofluorocarbons, which were then replacing chlorofluorocarbons. And we developed a structure-activity relationship, which now AI would do much better, between some of the properties of the molecules and their atmospheric lifetime. Don't tell me why it worked, but it worked remarkably well. It saved them a lot of money. They didn't have to spend £1 million for apparently it cost about £1 million each time to measure a rate constant, and it took about 5 minutes of the computer time.
Yeah.
You know, it's and that was one where we were able to take an applied problem and translate it into something we could do. But you know, it was it's varied. It's a very difficult. It was a very interesting problem, and we could talk about this for today.
Yes. It's a long discussion. Yes, I understand. Okay. Thank for answer your attention. Okay. Thank you. Bye.
Bye.
Thank you, Mario, for your questions. Then finally, let's move to Peru with Professor Henry Moncada from the Universidad Nacional del Callao. Henry, do you have any questions?
Yes, another one who is not in the field. So my question is, you talk about heavy metals, and these are in combination with nanoporous materials. How well they work to remove material, for example, like mercury? I ask me this question because my country is a lot of illegal mining.
Yes, and you have that problem too. Yes,
right. So, how well these technologies work? I believe that you need to combine more than one more technology to improve, but how well they work?
Right. Well, actually, I'm going to answer this question, and then I'm going to hand you over to Sergio, our coordinator, to give his opinion, because this project is with him. Is largely with him. In the lab, they work very well. The last slide, I gave a slide which gave you 100% removal of mercury and bismuth and the other nasty elements. Now, but of course, like with everything, you're asking a technological question about how is that going to work in a stream coming off from your gold mine, and how will the engineering work? And I can't really answer that. I can just tell you that the chemistry will work, and Sergio has there are a lot of mining engineers at Sergio's university who are confident that we should be able to scale it up. I don't think for me, one of the major problems is really the recycling, which currently requires Sergio, correct me if I'm wrong. You recycle at the moment by treating it with hydrochloric acid. That isn't an ideal method, and they work for about 3 or 4 times. You can recycle them 3 or 4 times, and then they're not so. Then they're losing their power to do this. Sergio, can I hand that question over to you? And you can answer in Spanish if you like.
The thing is, at the moment, we have a lab scale prototype. That lab scale prototype is working perfectly. But we need more funding for trying to scale up. When you scale up, so you don't have any chemistry problem. You don't have chemistry problem anymore. So the problems become more engineering problems.
Yes.
So you need to collaborate with engineers. So at the moment we are trying to do that. So from how to link a lab prototype with pilot plant and trying to design something far away from the lab scale. By the way, so I met Henry last year in Peru, so probably we can talk about that, Henry, if you are interested, so I can give you more details.
Thank
And
you, thank you. Yeah, I am interested
as
actually.
Neil said, so podemos hablar en español y nos podemos escribir en español. So at the moment, so Henry is collaborating with us. He is going to use our computational cluster for doing some calculations. So from that, we expect to strengthen our collaboration with Peru. So
Yeah, thank you. I appreciate that.
Excelente.
so now, so we have also some guests invited by Professor Neil Allan. I don't know if you would like to add some comments. So I think Rosario wrote something in the chat, but Ricardo or Rosario, would you like to add something? Or?
Just to say hello and thank, because the talk was wonderful, really nice. I worked long ago with him, so this reminds me those nice days in Bristol. Thank you.
Thank you very much for coming along, Rosario. Thank you very much, Ricardo, too, for coming along, and Stella too. Stella is also on the call.
Okay.
Just to say, I've started working with South America now. It was over 30 years ago. And first of all, we started with collaborating with Argentina, with Buenos Aires, with quite a lot. So it was lovely.
Okay. Yeah, thank you for being here. So Ricardo and Rosario. Jimena, Melvin, ¿hay algunas preguntas del público? Are there some questions for the social network?
Good morning, Professor Sergio. Good morning, Professor. We don't have any questions from our network, social network, sorry. The people only said the interesting topic that you point here in your talk. And also, I have to say thank you because this talk, it was interesting, so interesting. And it is so complement to some results that I have in my research. I only have to say thank you, Professor. We don't have any question for him.
Thank you. My pleasure.
So, Luis, would you like to add some final remarks about the network?
Thank you very much, Neil, for your nice talk. Just to briefly, this is the Latin American network of matter condensate physics or material science, which got many researchers from Latin America, and we organize talks every Saturday this time. For example, next Saturday is going to give Professor Gabriel Garcia Zambrano from Simvestab. The talk is experimental band gap prediction for semiconductor oxides 2000 of crystallographic structure, systematic comparison of machine learning methods. You are invited to participate whenever you want.
Okay, thank you.
At the same time. Also, March 7th is going to give us one speaker from the University of Santiago de Chile, is Brian Lozano. The talk is óxido de cobalto para la oxidación de amoníaco. On March 14, Saturday, the talk will be by Dr. Reinaldo Atencio from IBIC, Venezuela. The talk is supramolecular architecture of platforms for solar photon capture and energy storage. On Saturday, 21st of May, the talk will be from Alejandro Colton from the Instituto Balseiro, Centro Atómico de Bariloche in Argentina. The talk is about turbulencia en paredes magnéticas impulsadas. Saturday, 28th of March, interplay superconductivity and charge density wave in intermetallic compounds from Eduardo Villar from CBPF in Brazil. Saturday, 4th of April is Quirmión from Juan Carlos Piña from the University of Pernambuco in Brazil. Saturday, 11th of April, micromagnetism Micromagnetism, Eduardo Saavedra, Santiago de Chile, en Chile, en Saturday 18 of April, tecnologías sustentables, cómo los carbons dot son transformados en ciencias de materiales. El profesor Antonio Chiavon from the University of SJ, Saturday 15 of April, Frank Moya from Peru, Saturday night of May, José Barba, University of Colombia, 16 of May, Alejandro Trujillo, University of San Marcos in Peru. On Saturday 13 of May, we have the speaker now in this room is Professor Divya Prashkai Rai from Mizoram University in India. He wants to say hello, I think. Divya, are you there?
Oh yeah, I'm very much here only. Hi, how are you?
Fine. Your talk is that time, okay?
Yeah, I'm sorry that my camera is not working, so that's why I have logged in from the two devices.
Okay. Anyway, but your talk is scheduled on Saturday, 23rd of May, okay? And we are
Yeah, I'll be
completed.
there.
We are completed until end of August, so you are welcome to join us whenever you want, Neil and everybody here.
Yeah,
Okay.
fine, thank you. Yeah, no, some very interesting talks you're going to have. So
Okay.
thank
Thank you very much. Cheers, Sergio.
So please now turn on your cameras to say goodbye to Professor Neil Allan.
To run your camera, please, and your microphone as well. Microphones.
Gracias.
So goodbye, Neil.
Thank
Bye-bye.
you, Professor Allan.
Thank you for your nice talk. Bye-bye.
Thank you.
Bye-bye. Ciao, ciao.
Yeah. Thank you. Bye-bye.
Bye.